So we are now arrived at one of my favorite lectures of the course. I think they're all great, but this one is particularly one of my favorites. And I think today it's also particularly salient because we're going to be talking about this notion of generative models or generative AI. And today we're in this moment where this word of generative AI has maybe been propagating a lot and creating a lot of buzz. But today we're actually going to dive in to learn the foundations of what this concept of generative modeling even means. And what that core is that we can build systems that not only look for patterns in data to make decisions about that data, but to actually generate brand new instances of data based on those learned patterns. And it's an incredibly powerful idea. And I think it gets really at the heart of, what we mean by intelligence and what we want these types of systems to be capable of doing. So let's start with a little quiz of sorts. I want you to take a look at these three faces and think about which one of these faces you believe is real. Is it face A? All right, maybe 5% of people. Face B? Slightly more, maybe 7-10%. Face C? Also, okay, I'm measuring these percents relative to the total population, not relative to each other. None? So yes, now everyone is getting more intelligent and I can't fool people as easily as in the past. But the truth is, yes, they are all fake. None of these faces is real. None of these people actually exist. In fact, they were generated by a generative model called a style GAN, and we're going to get to this type of architecture and how it works later in the lecture, sorry. But generative modeling, to start from a basic machine learning point of view, when we talk about types of machine learning models or deep learning models that we can build, we can make some classifications about what these models are actually doing in terms of the task, the objective that they're trying to learn. And very, very broadly, we can think of two classes of models. The first class of models that we've been talking about so far are what we call supervised models. And they perform supervised learning, meaning that we have data that is of the form of instances like images or sequences, so on. And each of those instances is associated with a label, something that we're trying to learn, a mapping between that data and that label. And the goal with deep learning, supervised deep learning models, is to learn a neural network that maps that function. This can be used for classification, regression, segmentation, and so on. Now, there's another whole class of problems out there in machine learning called unsupervised learning problems. And that's going to be our focus in this lecture today. And the concept is that with unsupervised learning, our goal is not necessarily to learn a mapping from input X to output Y, but to just look at X on its own and try to learn patterns and features that define that data distribution, learning the underlying and hidden structure to the data. And this is not necessarily something that's exclusive to deep learning and neural networks. There are other techniques in stats and machine learning that can perform this type of unsupervised analysis. And the idea here is that with this concept of learning the underlying structure to data, what we're ultimately trying to do is to build a neural network that captures something about the distribution of that data and learning a model that represents that distribution. What that means and how that is realized is in two principal ways. The first is we can try to build models that perform what we call density estimation, meaning that these models are going to see a bunch of different samples of data, and they're going to learn to try to fit a function that models the probability distribution associated with how those data fall in some space, right? The other thing that we can do is we can take this learned distribution, this learned probability density, and then try to now say, okay, what if, because we have this underlying probability distribution, I draw new samples from it? Can I use this sort of sampling operation to actually generate new data instances? And this is this notion of sample generation. And the common point to both these use cases of generative modeling is this question of how can we learn a very good model of the probability distribution that is similar to the true probability distribution of our real data, right? And so it's a very, very powerful idea and a framework that's useful in a lot of different settings beyond just, generating images of people's faces. In fact, we can actually use generative models to do more intelligent learning of the algorithm and the model itself to use this information about what aspects of the probability distribution are more represented relative to others to actually train models that are more fair, less biased with respect to how they perform on particular facets of the underlying data distribution. And the concept here is that the model is only going to be as good as the data it sees, traditionally. But if we can use the information about what aspects of the data are more represented in the overall population, we could try to think about how we can create more fair and representative data sets based on these learned features. And this is something that you're going to get hands-on experience with in Lab 2 of the class. Another use case for using these probability distributions and learned generative models is in the context of outlier detection, right? Oftentimes we have settings where we want to really be able to preemptively find failure modes, right? So in the self-driving car example that Alexander previously introduced, there are going to be some instances, that could occur on the road that are very, very rare but are really critical. Let's say a person walks in front of the car or an animal crosses the road. You want the model to be robust to be able to handle those instances. And so by modeling this probability distribution, we can detect automatically, is this new observation an outlier, or is it falling squarely in the middle of the probability distribution? And then use this information adaptively to improve the model itself. So this is kind of a flavor of what types of applications these generative models can be useful for. And in today's lecture, we're going to specifically dive deeply into two classes of models. They're both what we call latent variable models. And we'll dive in, look at the architectures, give you a sense of how they work, and ultimately try to convey, again, the fundamentals and some of the math behind these types of modeling frameworks. So before we get to that, I think it's really, really useful to have a core understanding of what we mean by a latent variable. And the example that I love to use and always use to illustrate this is this story from Plato's work, The Republic, dating back many years back to ancient Greece. And this is known as the myth of the cave. And in this myth, there are a group of prisoners, and they're forced to stay in this cave and asked to just face a particular wall of the cave. And the prisoners are subject to being imprisoned, and they're forced to only actually observe things that are projected in front of them on the wall of this cave. So what they're seeing is shadows of objects that actually exist behind them, and they're only seeing the shadow projection that appears in front of them on the cave wall. And so to the prisoners, right, these shadows are their reality. They're the only things that they're observing. But we know that in truth, there's actually something behind them that is what is casting the shadow that the prisoners observe. And this is this notion of what is an observed variable, the shadows, and what is a latent variable, something that's hidden, something that's underlying and actually driving the structure of the problem. And of course, this is an analogy, but it gets at this intuition that latent variables are these underlying elements of structure to data that are the factors that are driving what it is that we're measuring and what it is that we're observing. And so our goal with generative models and latent variable models is to try to learn in an automated way something about a distribution that hopefully captures these underlying drivers or factors that are resulting in the observed data that we see. So to get at a sense of how we can do this from a deep learning neural network architecture framework, we're going to start by talking about a really simple generative model that we call an autoencoder. And the notion here is that we can take data and try to learn a lower dimensional encoding, some set of features that hopefully represents that data faithfully. And so what I'm showing here is an example with an image, the digit 2, and the autoencoder is taking examples of this data and trying to learn a lower dimensional feature space that is representing that in a completely unlabeled way. So maybe let's first ask ourselves a question here. If we're trying to learn a encoding, what I'm denoting here as the variable z, why would we maybe want to care that this set of variables z has a fairly low dimensionality? Yes?
Mislead us.
Eliminate redundancies. Exactly. Other ideas as well?
Efficiency, less than.
Efficiency, exactly. So the concept here is that we want to eliminate redundancy while being efficient to basically compress the data, right, to a lower dimensional encoding that hopefully captures a rich representation of that data. And so now the question is, how can we actually train a model to learn that lower dimensional encoding? The concept of the autoencoder is, well, okay, if we're going to start from high dimensional data like an image and move down to low dimensional data, maybe we can use reconstruction of the data as effectively a task, an unsupervised task, to teach the model to learn this encoding. So the concept here is that the autoencoder takes, let's say, an image, compresses it down to this lower dimensional encoding space, and then performs a decoding back all the way up to the dimensionality of the original data space. And so effectively, you're learning this lossy reconstruction, right, between your input data and this predicted reconstruction that we're calling x hat. Now, right, because this reconstruction is imperfect relative to the original data, what we can do is we can train the network by comparing the input data x and the reconstruction x hat and just asking it, okay, learn to minimize the difference between the two. That's it. And this is done using that same type of loss and same objective that we saw, I think, back in lecture 1, something like a mean squared error, right? Which with an image just means compare pixel by pixel in the image. What is the difference between the original data x and the reconstruction x hat, right? So this is a very straightforward way, and importantly, notice that in this reconstruction operation, our loss is only dependent on the input data x and the reconstruction x hat. There's no sense of y. There's no sense of labels here, right? So the last step that I'm just showing schematically is, taking those individual layers like convolutional layers, abstracting them away in this diagram, and again, showing you this concept of auto-encoding the input, going down to a lower dimensional latent space z, and then decoding back out to the original data space via this reconstruction. And this is a really, really powerful idea that I hope you appreciate for a moment here, because what this lower dimensional latent space, this set of latent variables z, allows us to do is to learn a feature set that we have not observed directly, right? It's entirely learned by the network. But our hypothesis is that it's an effective enough way to be able to reconstruct the data back out, right? So when it comes to this earlier question of like, what's the dimensionality of this space Z? It turns out a really good way to think about this is this notion of orthogonality and also of memory bottleneck and compression, right? So depending on how big you choose that latent space, that encoding to be, the quality of your reconstructions and the quality of the generations you can get out is going to be different. So you can imagine the smaller and smaller you go, you're forcing a larger memory bottleneck, which means that you're going to ensure more loss and your reconstructions are going to be poorer quality. And so there's a trade-off there in terms of how good of samples you can get out and how small you make that latent space. So the core concept with this idea of autoencoding, right, is we're effectively forcing the network to learn this compressed latent representation, and we're doing this via this reconstruction loss, capturing as much information about the data as possible by having the network learn to decode back out. And this is the idea and where the name autoencoding kind of comes from. You can think of it as self-encoding or automatically encoding the data. Now, the same concept, right, of autoencoding down to this bottleneck latent layer is the basis by which we can start now introducing a little more power in our ability to actually generate new samples. And to do that, we're going to explore this concept of variation and variational autoencoders. Traditionally, with what we just saw, right, in this take X, reconstruct it out, this is kind of a very deterministic operation, right? This latent encoding Z is just like any other neural network layer, meaning that once it's trained, once the network weights are finalized, no matter how many times you put this input 2 in, if those weights hold still, you're going to get that same reconstruction out, right? It's a deterministic operation. It's not super useful if now you want to generate new samples, right? Because all the network has learned is to reconstruct. In order to get more variability and more sampling, what we need is to introduce some notion of randomness and some notion of an actual probability distribution. And the way that is done is via this idea of introducing stochasticity or sampling to the network itself. And this is the difference between a variational autoencoder and a standard autoencoder. And the concept here is now, in this bottleneck latent layer, instead of learning those latent variables directly, let's say we have means and standard deviations for each of the latent variables. Then now let us define what? A probability distribution for each of those latent variables. What that means is now we've gone from a vector of latent variables Z to a vector of means mu and a vector of standard deviations sigma. And so this is effectively putting a probabilistic twist and flavor on this idea of autoencoding, meaning that we can now learn these latent variables defined by a mean, defined by a standard deviation, and hopefully use this to now sample from those probability distributions to generate new data instances. Question? It's a great question. So the question is, do we assume that the distributions are normal? Short answer is yes, we do. And we're going to now transition exactly into explaining why that is a reasonable assumption to make. So now to get a little bit further into this, right? Now, instead of a purely deterministic setup, we have these two halves to this VAE autoencoder framework. First, we have what we call an encoder, what's shown in green. And second, we have a decoder, shown in purple, right? All the encoder is trying to do is take the data and compute a representation of a probability distribution of these latent variables given the data X. The decoder does kind of the inverse. Now, operating back out, given those latent variables, can we learn the distribution of the data X? And these two networks, the encoder and decoder modules, are defined by their own sets of weights. Phi here represents the weights for the encoder component, and theta represents the weights for the decoder component. The next step is to define an actual loss function, an objective that will allow us to learn this network and optimize the VAE. And to break that down, we're going to look at two components to that. There's first this reconstruction loss, which is going to be very, very similar, if not exactly equal to the autoencoder loss that we introduced previously. But now we're going to introduce a second term that gets at this probability aspect a little more. So first, let's remember that we're trying to optimize our loss with respect to the weights phi and the weights theta. The first component, right, is that reconstruction. With an image, we can look at our input data X, the reconstruction X hat, directly compare them pixel-wise, and compute this reconstruction error. Now, we have to introduce another term that gets a little bit more interesting, what we call this regularization term. And the reason for that is we need to make some assumption, as the question asked, about what this probability distribution actually looks like. Effectively, what is done with regularization is we have to place a prior, a guess, a hypothesis on what we expect this distribution of latent variables z, defined by mu and sigma, to be like. The regularization term is then saying, okay, now we're going to take that prior and we're going to compare how good the representation learned by the encoder is relative to that prior. How close does it match our assumption about, let's say, a normal distribution? And the concept here is that it's learning kind of the distance, it's capturing the distance between the learned distribution, the inferred latent distribution Q, and some prior we have, some guess we have about what those latent variables should look like, right? Now the question comes, how do we choose that prior, right? Question, yeah, how do we choose that prior? So the most common choice, and what's done very, very, very frequently in practice, is to assume and place the prior of a normal distribution. What that means is it's normal Gaussian, meaning that we assume each latent variable is centered with mean 0 and has a standard deviation and variance of 1. And the rationale here is that it's going to encourage the model, hopefully, to kind of distribute the encodings of these latent variables roughly evenly around the centered latent space. And we can further try to penalize the network when it tries to cheat and diverge too far from this prior. I'm going to go into kind of a more intuitive explanation of why this normal distribution prior makes sense. But first, briefly, very briefly, to touch on kind of what the form of this regularization term actually looks like mathematically. There's this metric that we call the KL divergence, which is effectively a distance function that says, I have one distribution and I have a second distribution. How closely do they match, right? That's all this KL divergence is trying to compute. When we place the prior of a normal Gaussian, the KL divergence takes a pretty clean form, shown here. Don't need to concern yourself so much with the details, but should just kind of know conceptually that the concept here is we're trying to look at the distance and help regularize the network to try to minimize the similarity between, minimize the distance between the prior and the learned latent distribution. So now the question that's been raised a couple times, right? How do we choose this normal prior? Why do we choose it? And what does it effectively do? So to break that down, let's consider, right, what properties we want this technique of regularization to actually achieve. The first idea is that we want our latent space to be continuous, meaning that points that are close together in this latent space Z should hopefully be similar, meaning after you decode back out, the related content, related images. So let's say images, multiple different types of twos, for example. Secondly, when we go to use our VAE to actually sample, we want to have completeness, meaning that whenever we draw a sample from the latent space, hopefully we get something reasonable back out, right? We don't want samples to result in something nonsensical. And so with these two criteria in mind, the concept is that without regularization, we can sacrifice both these we end up sacrificing both these properties. Things that are close in the latent space may not be similarly decoded, meaning there's lack of continuity. So for example, if we have, this green point here, this orange point in the latent space here, one may end up decoding back a square with one point and a triangle with another point, but they're yet similar and close in the latent space. So objects that are actually dissimilar are close in the latent space, and we don't want that. Rather, we want things that are similar to be close in the latent space. If we impose some form of regularization, what this affects and amounts to is that now points that are ending up close in the latent space are similar when they're decoded, and they're decoded meaningfully. We're going to get both roughly triangle shapes out with these 2 points that are located very close to each other in the latent space. That gives us a sense of why regularization can be useful. Why does the normal prior help us? Is because of the fact that without this regularization imposing the normal prior, there is not so much of a structure in terms of what these distributions of the latent variables actually look like. Meaning that you could get very, very small variances that end up to pointed distributions in the latent space. Meaning you're going to get different means when you try to sample, you're going to get discontinuities. And furthermore, on the inverse, if you have very, very large variances, then this kind of destroys any sense of difference, right, when you have things that are just covering the latent space very broadly. So again, illustrating now visually, if we get very pointed distributions from not regularizing, having a small variance and different means, this could lead to discontinuities that we don't want. The high-level intuition with the normal prior is that it imposes this regularization to be roughly centered mean 0, standard deviation of 1, to try to encourage the network to satisfy these desired properties of continuity and completeness. Okay, any questions on that? I know it's kind of a hard intuition to wrap your minds around. Yes?
Is there a fundamental relationship between weights and so on in the decoding that's learned from the encoding?
Yes, so the question is there a fundamental relationship, weights in the decoder and weights in the encoder? The answer is yes. And that is because the network is learned completely end-to-end. Meaning we don't train the encoder separately and the decoder separately. We learn them all at once. So they're fundamentally linked, and that linkage, that pattern of linkage, is what is actually learned by the model in training.
Like completely abstract? Is there anything physical, or do we even like look at the hidden variables, or like just whatever?
Absolutely. So the question is, how can we interpret the latent variables, right? The answer is we can interpret them, and they're not necessarily always abstract. In fact, that's kind of the whole point of doing this encoding and this representation learning type of approach, is you want to try to extract some notion of structure in those latent variables, but do it in a data-driven way, right? And so I'll show a technique of how we can do that. One way you can start to interpret the latent variables is hold all but one fixed, right? And then effectively change the value of that latent variable, holding all the other latent variables constant, decode, reconstruct the input based on that perturbation, and then examine what are the instances you get out. How are they changing? And use that to now kind of back interpret what that latent variable was capturing. And I'll show an example of this, and it's also a hands-on example in the software lab. I know there are a couple questions, but I'm going to keep progressing. To the first question, our next point and section of this lecture gets at this notion of how we actually train this model end-to-end to learn these sets of weights, right? We have this loss function that comprised of the reconstruction term and the regularization term. And our goal is to learn these sets of weights completely end-to-end using this loss function. There's a problem, though, and a little bit of a nuance here, in that by introducing this notion of sampling and the mean and standard deviation terms here, it's not immediately clear. We don't have a direct solution of how we can backpropagate gradients when we want to capture something probabilistic. And so with VAEs, they employ this really clever trick that effectively diverts the sampling operation to reparameterize the latent variable equation slightly so that we can train the model end-to-end. So rather than saying that our latent variable z is directly the sample of a normal distribution defined by mu sigma squared, we say, let's offset all the randomness, all that sampling to this other variable epsilon, and say our latent variables are now the sum of a fixed vector of means mu and a fixed vector of standard deviation sigma, but that's now scaled by some random constant, which is going to be drawn from a prior normal distribution and is effectively going to capture the stochasticity that we want out of our sampling operation. Right, fixed mean, fixed standard deviation vector. And as a result, this effectively now diverts the sampling operation away from the latent variable z, where we cannot prior backprop through, but rather we can learn a fixed set of means, fixed set of standard deviations, and then divert the stochasticity to this variable epsilon. This allows us to now backpropagate gradients through and directly learn the latent variables via this mean and standard deviation vector. So this is called the reparametrization trick of a VAE, and it's ultimately the solution to allow the network to be trained end-to-end. Now, when it comes to having a trained VAE, a trained model, and trying to understand this question of what do the latent variables actually represent, what we can do is keep all variables except for one fixed and slowly perform a perturbation, changing the value of that single latent variable incrementally, and using the decoder component to now decode back out to our original data space. And so in this example with the face, you're seeing that come to life, right? Where the face is being reconstructed following a perturbation of a single latent variable that hopefully you can see is capturing the head pose, the tilt of the face in the image. And so what this kind of gets at is now the different dimensions, the different latent variables are trying to encode these different features that are hopefully interpretable. Ideally, right, with this idea of orthogonality and feature learning, you want those latent variables to be as orthogonal to each other, as uncorrelated to each other as possible. Because then you're maximizing the amount of information that your model is learning across this few set of latent variables. And this is this notion of disentanglement. And it's a very common question in training these VAE type models of how you can disentangle distinct latent variables, something like head pose versus smile in this example shown here. Turns out, in practice, right, there's a pretty straightforward solution to actually encourage disentanglement when you learn a VAE. And the solution is to basically relatively weight the reconstruction term relative to the regularization term and tune the relative strength of these two components of the loss to encourage disentanglement. And there's this slight variant of a VAE called a beta VAE that just says, okay, if we put a weight on the regularization term that's greater than 1, it can constrain the latent bottleneck to basically be encouraged to disentangle these distinct variables such that now you can get more interpretable and better disentangled features with greater weights on the regularization term. And so there's more details in this paper that go into the math of why this works. But the concept is by imposing stricter regularization, you can now try to disentangle these variables more strongly. Okay, so to summarize this part of the talk and to wrap up this concept of latent variable models, you're going to get some hands-on experience in the software lab playing with these types of models in the context of computer vision and facial detection systems, and see how we can interpret these types of features and use those features to actually create better models that are going to be more fair and more unbiased. Finally, to close, right, the summary of the key points and concepts behind VAEs is that fundamentally, this notion of latent variable models is effectively trying to compress data into a lower dimensional encoding that we can use to both generate new samples and also understand the features underlying that data. This framework allows us for completely unsupervised reconstruction. We don't need labels associated with the data. We can use this notion of reparameterization to train the model end to end. We can interpret the latent variables via this perturbation analysis, and we can now use the learned latent variables to sample from that space and generate new examples. So with VAEs, the core is that this latent variable space is effectively an estimate, a representation of that probability distribution that I mentioned at the beginning, right? Sometimes, though, we want to prioritize the ability to generate very faithful samples while sacrificing our ability to learn those features in a more interpretable or probabilistic way. And so there's another complementary kind of class of models that we call generative adversarial networks, or GANs, that are more focused on this question of how can we just generate samples that are going to be very good, sacrificing the ability to decode and interpret a set of latent variables. And the idea behind GANs is rather than trying to explicitly model these probability densities, let's just learn a transformation from something very, very, very simple, say completely random noise, and now learn a model that can transform that distribution of noise to the real data distribution, such that we can then use that learned model to generate samples that hopefully fall somewhere in that real data distribution. And GANs initially introduced a lot of excitement about this idea of generation from completely random noise, which seems kind of wild when you think about it in that way, right? And the intuition behind GANs is pretty clever. The concept here is that we're going to put two components of the network, what we call a generator and what we call a discriminator, in competition with each other. They're going to act as adversaries. The concept here is that we're going to first have a generator component that looks at completely random noise and attempts to sample from this noise and, let's say, upscale it to the real data distribution. And at first, its generations are going to be pretty bad, right? They're not going to be very good. Then we're going to have another model, a discriminator, come in and look at those generated instances, compare them to real data and say, is this real or is this fake? And by linking these two together and training them jointly, the concept is, can we induce the generator to create better and better examples that will soon be good enough to fool the discriminator into not being able to tell what's fake and what's real? And they're effectively competing with each other, right, in this framework. And so to break down how this works, one of my absolute favorite illustrations, not only in this class, but ever, is as follows. And I think it gives hopefully a strong intuition behind how GANs work. So we're going to consider now this points along this line, right? We have our generator here on the right. It's going to start from completely random noise and try to create an imitation of data, right? Let's say now these orange points are those fake data samples drawn from noise. Now the discriminator is going to look at these points. It's also going to see instances of real data. And the discriminator, we're going to train it to, say, produce a probability that the data it sees are real or if they are fake. And in the beginning, right, it's not trained, its predictions are not going to be so good, but then let's say we train it, we show it some more examples, and it starts increasing the probabilities of what is real and decreasing the probabilities of what is fake. Now we continue this, right, training a normal classifier model, a discriminator model, such that using these real instances and these fake instances, the discriminator is perfect. It can perfectly tell us what's fake, what's real. Now the generator comes back, and it sees now where those real data instances lie. And the objective that we supply to the generator is move your samples closer and closer to these real instances. And so it can start doing that and generating new samples that are hopefully, if our objective is good, closer and closer to the real data. Now the discriminator sees these new samples and receives these new points. And now its decision is not going to be as strong. It's not going to be as clear. But again, it's estimating the probability that each of these points is real. Learning to decrease the probability of the fake points, increase the probability of the real points. Once again, we repeat this process one last time. Generator starts moving those fake points closer and closer and closer to the real data, such that the fake data are almost overlapping with the real data. And so if the discriminator were now to come back and look at these samples on the right, it's not going to be able to tell what is real, what is fake. And that would indicate that the generator has succeeded in learning an objective to generate samples that mimic the real data distribution. So this is the summary and the concept of this framework behind the setup of the GAN. where you have a generator component, this network G, that is trying to synthesize fake data instances to fool the discriminator, while conversely, the discriminator is trying to identify the synthesized fake instances from examples of both real and fake. And in training, right, the objective, the loss function that's actually set up for a GAN network composes these two competing objectives for the generator and the discriminator. And if we succeed in training the GAN overall, we would have reached an optimum where the generator is able to perfectly reproduce the true data distribution, and the discriminator has no power at all in classifying these instances. It turns out that in practice, this is pretty hard to do. GANs are notoriously very, very difficult to train. And in the years since, there have been a lot of works in the field that try to propose better loss functions, other tricks to stabilize the training of the GANs. But in practice, it's quite a difficult class of models to train. And so there's things that we can do to make GANs better, and there are also things that we can do to introduce new types of models that are going to be more robust and easier and more stable to train than this framework with GANs. So at the end, let's say we've trained our GAN model. Now what do we do with it? Well, to actually use the GAN to generate new instances, all we have to do is go back to the generator component of the model and now start with points in that noise distribution, pass them through the generator and sample to create new data instances. And here sample means just picking different points from the initial distribution of random noise. And so the concept here is that the GAN is effectively learning an effective transformation of a distribution, moving from Gaussian noise, pure random noise, to this learned target distribution. What is really, really cool is that we can think about how to traverse this space of this learned distribution, meaning that different samples from Gaussian noise are going to end up in different places in the data world, right? And the GAN is learning a mapping that allows us to do this transformation. And it turns out that you can actually traverse and interpolate in the space, in the starting space of Gaussian noise, and generate samples that can then be traversed across this across the target data distribution. And so the results of this are pretty cool because you can apply the same type of initial perturbation starting from your noise sample to then produce progressive, similar images, in this case, across the target distribution. So GANs are really, really a very neat framework to think about, and they are indeed the architecture that was used to generate some of those types of face images that I showed on slide 1, right? And there are different advances that have been proposed from a modeling perspective that allow better results to come from GANs. One neat thing that has been done that I'll spend a little bit of time on is thinking about now how we can better control the generative process of a GAN. Let's say we want to condition on some different types of information and generate samples accordingly. What we can do is not just supply only the random noise as the starting point, but also look at other forms of conditioning factors that can then guide the generations from a GAN. One core idea here is this notion of paired translation, meaning that we can consider now pairs of inputs, for example, a scene and a corresponding segmentation map, and now train the discriminator not to operate over only one, but rather pairs, and say, okay, what's a true pair of an image and a segmentation map versus a fake pair of an image and a segmentation map. And in practice, what this allows us to do is now do these conversions of paired translation, where the generator can take in an input of, let's say, a segmentation scene and generate the output of the real world view scene, or a street view map and generate kind of a grid view and different instances of how, day to night, black and white to color, so on and so forth, of this paired translation type of generation. A very common way that this is employed is in looking at maps and in translating between, let's say, a map view and an aerial view of an image, and vice versa. A very, very related idea is this notion of, now, what if we don't have just linked pairs, but we have two related data distributions? And again, we want to learn some relationship and transformation that links those two domains. And so an architecture that was proposed to do this is what is called a cycloGAN, which is now saying, let's say we don't have explicit pairs, but rather we have a bunch of instances in one domain and a bunch of instances in another domain, not paired. How can we learn a relationship mapping these two distributions together? And the concept of the cycloGAN is that we can basically impose a cyclic loss linking the discriminator and the generator in one domain to that of another. And so in this example here that I'm showing, what ends up being accomplished in practice is you can do these functions where, let's say, you have images of horses, images of zebras, and the model that's shown here is a cycloGAN that has learned a mapping from the horse domain to the zebra domain and is now generating those instances accordingly. So notice here, right, in this example, there's not only the transformation of the skin of the horse to stripes, but also the grass is looking different. It's less green. And so it's the entire transformation of the image distribution itself, right? Again, I think that this concept of now domain translation, domain transformation gets at this notion that GANs are very effective ways to basically learn transformations of data distributions. We can go from learning a transformation from Gaussian noise to our target data distribution, or with cycloGANs from one data space X to a target data space Y and back, right? And earlier in the prior lecture, there were some questions about how we actually generated that operates on images of spectrograms, which are the conversion of an audio waveform to a spectrogram image, and effectively we built a cycloGAN model that can transform speech from one domain to speech of another domain. So following this conversion of the audio waveforms to these spectrogram images, the cycloGAN was trained to perform this conversion. And specifically, what we did was we took recordings of Alexander's voice, Alexander speaking, converted them to spectrogram images, built our cycloGAN model, took the recordings of Obama's voice, did the same thing, and then learned the cycloGAN model to perform this domain transformation between audio of Alexander's voice and audio of Obama's voice. So today we've talked about these two classes of deep generative models, specifically focusing on latent variable models that can learn these lower dimensional representations and encodings of the data, and then this concept of putting these adversarial networks together to now be able to generate new data instances. So VAEs and GANs are really kind of the two deep learning frameworks that brought generative modeling and generative AI kind of to life a few years back. And since then, right, the field has really expanded, taken off. And there is a particular class of models that have led to quite tremendous advances in generative capabilities, not just in images, but in many other domains. And so this is an instance, an image instance from one such model, which are a class of models called diffusion models that are very closely related to VAEs in the concept and how they're built, but they have this ability to be able to generate new instances with very high fidelity and also be guided and conditioned on different forms of input like text or other types of modalities to really be able to impose more control over the generative process itself. And so tomorrow we're going to talk about how these models work and talk about uses of them not only in images but other domains as well. So with that, I'm going to close out, getting some hands-on experience with these latent variable models in the context of computer vision and in the context of facial detection in particular. Thank you.